This chapter deals with unified growth theory, and it's based upon two articles. The first is by Oded, Galor, and David Weil, published in 2000, Population, Technology, and Growth, from the Malthusian Regime to the Demographic Transition and Beyond, which was published in the American Economic Review and is the founding paper actually of unified growth theory. Then in 2005, Oded Galor wrote an article for the Handbook of Economic Growth. It's chapter 4, From Stagnation to Growth, Unified Growth Theory, in which he summarizes the research up to that point and also provides some extensions to the basic model. And finally, a nice textbook treatment is, of course, the book by Oded Galor, Unified Growth Theory, which contains many of the extensions and really a lot of evidence on unified growth theory and how it can be tested basically and what these tests on the data say. The starting point for unified growth theory is the observation that over most of human history, economic growth was an unknown phenomenon. So here, for example, I've taken a graph from the website Our World in Data, which you can access under this link. And you see per capita GDP over the last 2000 years for the United States, Austria, France, the United Kingdom, South Korea, Argentina, China, Indonesia, and India. And what we see here is that until the Industrial Revolution, there was actually no per capita GDP growth. The countries were all rather similar, all were rather poor, and the people living in these countries, or most of them except for the elite, was living at subsistence levels. Then, when the Industrial Revolution occurred, first in the United Kingdom basically, growth started to emerge. Positive growth rates started to emerge, and after the Industrial Revolution, since then, these countries experience sustained economic growth. Sustained in the sense that economic growth had been positive since then in these countries. And what we can also observe is that some countries were earlier with their takeoff, such as the United Kingdom, but also the United States and some Western European countries, and some experienced the takeoff much later than the other countries, which led to a certain divergence of income levels. So when income was rather similar in these countries before the Industrial Revolution, huge gaps emerged afterwards, which were called the Big Divergence actually. We can see this even better by zooming in and taking regions instead of countries. So we have here the Western offshoots, which are the United States, Canada, Australia, and New Zealand, Western Europe, Eastern Europe, the Middle East, East Asia, Latin America, South and Southeast Asia, and Sub-Saharan Africa. And we observe these regions not over 2000 years, but over the last 200 years now, from 1820 to 2020 roughly. What we see here is again that these regions were comparatively similar in terms of their regional per capita GDP at the beginning of the Industrial Revolution, but nowadays these countries differ to a large extent. The Western offshoots and Western Europe experienced the Industrial Revolution first. They experienced positive economic growth, and the growth rate even accelerated here in this time period, and nowadays they are the richest regions. Other regions had their takeoff much later, for example, Eastern Europe and also East Asia, where East Asia had its takeoff basically after 1950, and its huge increase is mainly explained by the fast growth of China's economy then in the last couple of decades. And then we have countries in Sub-Saharan Africa, and therefore the Sub-Saharan African region altogether, that did not yet experience such a sustained take-off to economic growth yet. So economic growth rates had been positive here in the last 2 decades, but it was not so high that they would have caught up with the rest of the world in terms of per capita GDP. So the different timing of the takeoff, as I said before, explains this great divergence across regions, but also across countries within regions. Now, these observations trigger a lot of different questions. First, why actually did per capita GDP stagnate before the Industrial Revolution, and why was it growing in a sustained manner since then? What triggered the takeoff to sustained long-run economic growth, in the different countries, and we will see that this crucially depends on the demographic transition. So we'll also ask what the role of the demographic transition is in this process. And particularly, we are also interested in the explanation for the differential timing in the takeoff across the different regions and countries, and therefore what explains this emergence of the Great Divergence. And this is where Oded Galor's and David Weil's ideas come in, where the idea of unified growth theory is basically to capture the developments that we've seen so far within one single mathematical framework that can explain the three phases that we've observed within one coherent mathematical model, basically. So we've observed the Malthusian stagnation, then a takeoff to economic growth, which is the Industrial Revolution and the demographic transition, and then a phase of modern economic growth, including the divergence of the different countries and regions. And the interesting idea here is to really get this within one single dynamic framework, because we would have the Malthusian theory before the Industrial Revolution actually explaining stagnation, and we would have modern growth theories such as endogenous economic growth theory and everything that we've talked about in this course until now after the Industrial Revolution. But actually we want to have them together, explained within one mathematical framework, and that's the reason why it's called unified growth theory, because it brings together these separate building blocks. Now, what we will observe here is that technological progress as the main driver of economic growth is driven by the size of the population in earlier periods. So we have a certain type of scale effect in earlier periods, which is consistent with empirical evidence, but this scale effect vanishes later on when investments in human capital became more important. So later on we will have that it's not the size of the population that drives economic growth, but rather the education of the population and the human capital that they have. And in this kind of change over time, we will see that the fertility transition plays a very important role. The reason is that before the Industrial Revolution and before the demographic transition, fertility rates and mortality rates were high in all countries. That means high fertility was balanced off with high mortality. So families had many children, but many of these children died before reaching their fifth birthday, actually. And only then, during the demographic transition, the mortality rate decreased rather dramatically, and that led to a temporal increase in the population growth rate when fertility hugely outweighed mortality. But then, after a certain lag, also fertility rates decreased, and families chose to have fewer children in response. And that led to actually a reversal in the relationship between income and population growth or fertility, because before the Industrial Revolution and before the demographic transition, an increase in income of a household led to a higher fertility rate. And actually there was a positive correlation between income growth and population growth. And this led to a situation where all technological progress that happened, which increased incomes, was counteracted by the increase in population growth, which raised the number of people and therefore the denominator in per capita GDP, and it raised it to a faster rate than technological progress, bringing economic growth again down and to a halt, and therefore having economic stagnation. However, then during the demographic transition, the positive association between economic growth and population growth changed and reversed, such that after the demographic transition, actually higher incomes of families was associated with fewer children in the families. So there was a transition from quantity towards quality, as we will see later, where families rather invested their higher income than in education of their children and not so much in having more children. And this led to this reversal in the relationship between income growth and population growth that actually enabled this economic takeoff, as we will see later on in the dynamics of the model. Now, the description of the model follows actually the depiction in the paper by Galor, published in 2005. And here the production side is as follows. We have a constant returns to scale production function in the two inputs, land, which is a fixed supply, and labor. And on the household side, we have a two-period overlapping generations model, where the childhood period is actually a passive period in which children do not make any economic decisions. But in adulthood, individuals decide on how much they want to consume, the number of children they want to have, which is the quantity of children, and the education of the children, which is the quality dimension of children. Now the production function is Cobb-Douglas. Output is denoted by Y. The subindex again refers to time. And output or income, which is the same here, it's a closed economy, is produced by human capital with an output elasticity of alpha and effective resources with an output elasticity of 1 minus alpha. What are effective resources? X is the amount of land in the economy, which is fixed, so it has no subindex with respect to time, but it's multiplied with the technological level at time t. So if the technological level increases, I can produce more agricultural output out of the land that I have. And then the per capita production function, per capita GDP or per capita income, is this production function here divided by LT, the number of workers. And that means that per capita output is given by per capita human capital to the power of alpha and per capita effective resources to the power of 1 minus alpha. Now, there is a simplifying assumption made by Galor and Weil, and that is that there is no property rights on land. So the agricultural sector is interpreted as being composed of family farms. So the return on land is zero, so there is no compensation for land, but the workers on land earn the average product of human capital. So the remuneration, the wage per unit of human capital, is the average product of human capital. So it's xt divided by ht to the power of 1 minus alpha. The reason is that in a family farm, the members of the family work on the field, and the total income that is generated out of that is distributed among the family members. So it's not this standard way of thinking that we have with the marginal product being the compensation, but here the average product if we interpret it as family farms. The utility function is also Cobb-Douglas of households, and utility is assumed to increase in consumption, where basically the exponent of consumption is 1 minus gamma, and the number at the human capital of children with an exponent of gamma. And that's basically that utility of households increases if they have more children, ceteris paribus, or if their children are better educated, ceteris paribus. So what I derive utility from is own consumption, number of children, or human capital of the children. And the budget constraint looks like this, where we have parental income on the left-hand side if they would supply their whole available time on the labor market. So then parental income would be the going wage rate, WT, multiplied by the human capital that parents supply on the labor market. However, raising children is time intensive. So if people want to raise one child, then tau is the fixed cost per child actually in terms of parental time of raising them. So what we have to subtract here from that is the time that raising a child costs the parents. And if they have more children, then of course this fixed cost of children increases. However, the cost of children are also education outlays, and also here it's assumed for the sake of simplicity that this comes in terms of parental time that is invested in educating the children. And this is not a fixed cost, but it increases in the education that I want to provide my children with. So this is basically the parental time invested in education and for raising children as such. And we have consumption expenditures here. So altogether, consumption expenditures plus the time invested in children in terms of raising them without educating them and in terms of educating them must not exceed the full parental income if they were to spend the whole available time on the labor market. Now, what about the production of human capital? Here, the assumption is that human capital of the next generation, so of today's children when they are adults and supply their labor on the labor market, depends on the education that the children get now from their parents and from technological progress in the next period according to a certain function h. And this function h is increasing and strictly concave in education. That makes sense. So if children get more education, they will ceteris paribus have a higher human capital stock when they are adults. But the effect of education diminishes basically. So the first unit of education increases human capital of the children later on in their lives more than the 10th unit of education, and so on and so forth. And then the function h is decreasing and strictly convex in technological progress, gd plus 1. So if technologies progress faster, then a given amount of education is worth less because it basically gets obsolete due to technological progress. And then Oded Galor puts some assumptions on the cross derivatives, namely that the derivative of the function h with respect to e and the second derivative with respect to g is positive, meaning that education has a stronger effect on the human capital of the children if technological progress is faster. And then the function h is normalized to 1 at the point where children get no education and there is no technological progress. So that's basically when this function is normalized. Now this optimization problem can be written down and afterwards solved. So the household's optimization problem is to maximize utility of the parents, which is basically determined by consumption and fertility and human capital investments, where the human capital investments et plus 1 lead to a certain human capital level ht plus 1 in the next period. So that's according to a Cobb-Douglas function. Then the budget constraint is substituted in this expression for consumption. And here basically we see that utility is concave in all the inputs, so we know that the budget constraint will not be fulfilled with a strict inequality. It will be fulfilled with a strict equality, and then we can just express consumption as a function of parental income and the costs of children in terms of time units, and substitute this into the consumption expression in the utility function, the maximization problem. And then we have a maximization problem in the two variables fertility and education in the next period. And here, for human capital at time t plus 1, we substitute in the function that we had on the previous slide, the production function for human capital. Well, and then this will be maximized, subject to the conditions that the budget constraint holds, and in addition, that the consumption that is left over when I subtract the time requirements for educating the children and raising the children is greater or equal to a certain subsistence consumption level C tilde. The C tilde is what people need, otherwise they starve to death. So it's subsistence consumption. It has to be fulfilled, irrespective of how high income of households is. So if households have a rather low income level, they will first look to satisfy their subsistence consumption needs, because otherwise they will die. And only the rest of their income that they do not need for fulfilling their subsistence needs is used to invest in the quality and quantity of children, basically. Then the fertility rate is non-negative, which is clear, and also education investments in children are non-negative, so that's intuitively clear. Next, there is a certain threshold level of income denoted by Z tilde, and it is referred to as subsistence income. It's equal to C tilde divided by 1 minus gamma, and this threshold actually determines a kink in the income expansion path, as we will see later on. So as long as incomes of households are above this subsistence level of Z tilde, the fraction of time spent on rearing children would be gamma, and the fraction of time spent on the labor market to afford consumption goods would be 1 minus gamma. So the standard Cobb-Douglas shares, the optimal shares of resources, in this case time, that I would spend on the different goods in the utility function. Now, if income is below the subsistence level Z tilde, however, households would do everything to fulfill their subsistence consumption needs first, because otherwise they would starve to death. And only if certain time resources remain over, they will spend this on raising children, either rearing them or on education. So this is basically what we have here. So the time spent on children, or the fraction of time, would be gamma if actual income is above the subsistence income z tilde, and it would be 1 minus c tilde divided by zt if actual income is below z tilde. And this leads to the following income expansion path that we can describe in this diagram, where we have consumption on the horizontal axis, the fraction of time that households spend working such that they can afford consumption goods. And on the vertical axis, we would have the fraction of time they spend raising their children. Now, we assume in this first situation that the budget constraint looks like that. So we have a rather poor household, and all points on the budget constraint that are located to the left of C tilde, they are not feasible, because otherwise the household would just starve to death. So in this case, the household would choose a lower consumption level than the subsistence level, and therefore the household would starve. And that means that the optimum is not necessarily where, is not in this case, where the budget constraint is attentioned to the indifference curve. In this case, it's rather a constraint optimum where households spend C tilde, or the time that they need to afford C tilde, working on the labor market, that only the rest they can spend on raising their children, which would be basically this part here on the vertical axis. Now, as incomes increase, the budget constraint would rotate counterclockwise here around this point 1 here. And in this case, it's drawn such that actually this point becomes affordable. So households would increase the fraction of time they spend rearing children if income increases here, but they would not increase their consumption because they fulfill their subsistence needs already, so they do not need to increase consumption at that point. But the optimal thing to do here would be to increase the fraction of time spent on children. And as soon as they reach this point here, the income expansion path becomes horizontal. So if incomes rise further and there is a further counterclockwise rotation of the budget constraint around this point here, then we see that the fraction of time spent on working and the fraction of time spent on raising children both stay constant, and additional increases in income just lead to more consumption expenditures as such, and more expenditures on children in terms of the opportunity cost, but not a higher fraction of time spent on raising children. So that means the income expansion path is first vertical until this point is reached where the budget constraint is attentioned to the indifference curve, exactly at the kink of the income expansion path, and then the income expansion path here becomes flat or horizontal. So as incomes increase, households would here raise the fraction of time spent on child rearing, and from here onwards the fraction of time spent on child rearing would stay constant. So now we can say a little bit about the optimal choice of households with respect to the fertility choice and the education choice for their children. So here we've already seen that the amount of time spent on child rearing will differ whether household income is above Z tilde or below Z tilde. And that's also, when we calculate fertility, a consequence of that is that if the income level is above this subsistence income level Z tilde, then households will choose a fertility rate that is given by gamma over tau plus E as a function of GT plus 1. And this is denoted by Oded Galor as NB, which is a function of the growth rate of technologies here, because education is a function of the growth rate of technologies. So that's when household income exceeds subsistence income. If it is below subsistence income, however, households do not spend the full fraction of their time gamma on children, but only 1 minus C tilde over Z. So the numerator here is 1 minus C tilde over ZT instead of gamma. The denominator stays the same, but here we see that the resulting fertility rate, which is denoted by N superscript A by Oded Galor, is now not only a function of technological progress, but also of the income level of households, because the numerator here depends on the income level of households. So we have two different cases to consider with respect to fertility, either the case when incomes are low or the case when incomes are high. And for optimal education of children, it's the same. So optimal education is actually a function of technological progress. If technological progress is rather low, so below a certain threshold G hat, then education investments of parents in their children will be zero, because then it does not pay off to invest in education of children, because technological progress is not fast. So the world is not so sophisticated, and therefore education does not pay off. But if technological progress is fast, above a certain threshold level, then education investments will become positive. Parents want their children to participate on technological progress and to have higher wages, and then the optimum for them would be to invest in education of their children. So this functional form, ET plus 1, is positive. So the first derivative is positive, meaning that educational investments, ceteris paribus, increase with faster technological progress. The second derivative is negative, so it's concave actually, and this holds for all gt plus 1 that are greater than g hat, because if gt plus 1 is lower than g hat, then education is just 0, so this would be equal to 0 then. Then we can perform some comparative statics on the optimal solution. The first one is a change in the growth rate of technology, which would lead to a decrease in the growth rate of the population. We see this from here. If the rate of technological progress increases, that would raise education investments, and therefore it would increase the denominator in both expressions, irrespective of whether I'm in this situation or in this situation. So fertility would actually decrease with technological progress. Education itself, by contrast, would increase with technological progress. That's what we know basically from this assumption here. So it's rather trivial. So it's just that we have it for the sake of completeness. With respect to a change in the income level, however, we have to consider the differences between the two cases of whether the subsistence income constraint is binding or not. If the subsistence income constraint is binding, then actually an increase in income leads to an increase in fertility. That's what we see here. If incomes increase, then this term here decreases, and this term is subtracted from 1 in the expression of fertility, so this term would then become larger. So if this is the case, then fertility grows. With respect to education, however, we see there is no effect of increases in income, because education only depends on technological progress here. And then if the subsistence constraint is not binding, so the actual income of households is above the subsistence income level, then we see that both fertility and education do not depend on income, so here both derivatives would be equal to 0. Now we come to the dynamics of technology and education. First, technological progress. Of course, the rate of technological progress is given by its definition here, AT plus 1 minus AT over AT. And that's a function of education of the population and the population size. If the population is better educated, then the scientists in the society would be more productive. They are better educated. It's more likely that they come up with productive new ideas. And if the population size is constant, is larger, there are simply more scientists. So it's a standard scale effect that appears in this function here. Now the assumption is that with an education level of 0, there could still be technological progress, because it would be driven by the scale effect LT, and that's mainly relevant for early periods of technological progress, when technological progress did not depend so much on a joint effort and large laboratories and well-educated scientists, but more on tinkerers that tinkered around with something and came up with a new idea that increased technological progress. The function g is positively, so increases in both arguments, but at a decreasing rate. So that's what we have here. Then we can write down population size, the evolution of the population size, which is the fertility rate multiplied by the previous period's population size. And here we have to distinguish between the two cases. Case A, when fertility actually depends on income, and case B, where fertility does not depend on income, but just on education investments then, and education investments in turn depend on technological progress. Now in the first case, the actual income of households is lower than subsistence income, so the fertility rate is a function of the rate of technological progress via the effect of technological progress on education. and income, as we've seen before. And income itself is a function of technological progress, education of households, and the number of effective resources in the economy xt. So that would be the population size in case of a low income level. In case of a higher income level, the fertility rate would only depend on technological progress, as I said, so not anymore on Z, and then the population size would be given by this expression here. And then effective resources, xt plus 1, lowercase xt and lowercase xt plus 1, depend on technological progress. So it's the level of technologies multiplied by the fixed resources. And since it's per capita, so the lowercase x, we divide by the population size at time t plus 1. So that means there is a certain race between technological progress, which determines at plus 1 for a given at. So the faster technological progress is, the higher would be at plus 1 for a given at. And in the denominator, we have the population size, where the same holds true as before when fertility is higher. So LT plus 1 would be higher given LT if NT plus 1 is higher. So there is a certain race between technological progress and the fertility rate on whether effective resources increase. If fertility outpaces technological progress, then effective resources would actually go down, and only if technological progress is faster than population growth, effective resources would go up. And basically, that's a certain Malthusian thing here. So Malthus basically said that technological progress would never be able to outpace population growth here, and this can be kind of illustrated with such a such an evolution here. So then effective resources would be a function again of ET, GT, XT, and LT if incomes were lower than the subsistence income level, because their fertility still depends on income in this regime. And if income is higher than subsistence needs, then it does not depend anymore on technological progress and XT effective resources. It just depends on education and LT, because then what matters is GT here. Now we can summarize everything that we know up until now, and that results in two different dynamical systems depending on whether the subsistence constraint is binding or not. If the subsistence constraint is binding, we collect all the results that we had previously on the evolution of the different variables depending on the other different variables, and there we saw that income plays a role in determining fertility. And therefore, on the right-hand side of this system here that is written down in effective resources, education, technological progress, and the population size, we have all four variables. So education, technological progress, effective resources, and the population size. And we need to solve this four-dimensional system or simulate this four-dimensional system to get the dynamics of the economy. By contrast, if the subsistence constraint is not binding, this collapses to a three-dimensional dynamical system, because here we see that the population size does not anymore depend on income. And therefore we have on the right-hand side only education, the population size, and effective resources that matter. So we can write down the evolution of the economy in just these three variables. So we would have a system in terms of effective resources, education, and the population size. Irrespective of whether the subsistence constraint is binding or not, however, the subsystem for education and technological progress can always be analyzed independently of effective resources as long as there is a given population size LT. So then technological progress would be a function of education and the population size, or the number of workers, L, and education itself is a function of technological progress. And in the next few figures that I will show now, this subsystem is always shown in the phase diagram on the left-hand side for different levels of L. And on the right-hand side, we have the dynamical system, or the full dynamical system of the economy. And in these figures on the right-hand side, the frontier that actually separates the areas in which the subsistence constraint is binding or not, in terms of the conditional Malthusian frontier. So the conditional Malthusian frontier determines whether the subsistence constraint is binding. That's the case when we are below this conditional Malthusian frontier. And if it's not binding, we are above the conditional Malthusian frontier. And the loci EE and XX refer to those loci at which education and effective resources are constant, so where they do not change over time. So now we describe the dynamics of the economy in terms of the two dynamical systems, the subsystem on the left-hand side and the full system on the right-hand side. And the first case that we consider is the case of a small population size. Now here we would have the equation that relates to education in time period t+1, which is a function of technological progress, gt, which is on the vertical axis, and education is on the horizontal axis. And technological progress itself would be a concave function of education and the population size. Now we see here the population size is comparatively low, so this curve is located below the ET+1 curve here for all points in the interior of the graph. So the two do not intersect, and that means that irrespective of where we start, we would always converge to this point here with zero education and a comparatively low rate of technological progress. So that's the only point here where the two lines intersect. In terms of the full dynamical system, what we have here is the locus where effective resources are constant. And here we have the conditional Malthusian frontier. So below that, the income, the subsistence income constraint is binding, and above it, it's not binding. And the education locus would be here, where we would have constant education that is zero here for this case. Now, if we start somewhere here in this area, we would move down. So here education would decrease and effective resources would also decrease. And if we start here in this quadrant, education would actually also decrease, but income into effective resources would increase. So in this case, the economy would move up until it crosses the locus where effective resources are constant, and then the economy starts to converge to this point, where this point here is basically this point here. So education is zero and technological progress is rather low, and effective resources therefore are also rather low. If the economy starts here, then they would converge in this way to this point, and if they start here, they would converge from this way to this point. So basically this point is globally stable, which is also what we see here. Irrespective of where we start, we would also always converge to this equilibrium, which is in this sense a poverty trap. So the economy has a low growth rate, no education, and low effective resources, and irrespective of where it starts, it will always converge to that point. Now, what is the case for a higher population size, say a moderate population size? This equation now, the GT+1 curve, would shift upwards, because as compared to this situation here, we would see this curve would shift upwards, and it would then start to intersect with the ET+1 curve, basically multiple times. So we would have multiple equilibria here. That means that also in the full dynamical system, we have then multiple loci at which education stays constant. So if we are in this point, we would be along this curve, education would be constant, but rather high. If we are in this equilibrium, that would be along this line here, education would be low but positive, lower but positive, and in this point here, education would again be zero, so that would again be this point here. Now, it's interesting, namely, if we start to the right of this intermediate equilibrium here, we would converge to the equilibrium with the high education level, but if we start to the left, we would converge to the equilibrium with the low education level. So in terms of the dynamics of the full system, we would have that if we start to the left of this EE locus here, we would again converge downwards here and upwards here, so we would converge to this point here. Only if we start to the right of this equilibrium, we would experience increases in education and increases in effective resources. So here it would mean that if we are to the left of this locus, we would converge to the stagnation equilibrium again with low technological progress, low effective resources, and so on. If we are to the right, however, of this, we would experience convergence to a positive growth rate and no stagnation. So incomes and effective resources would rise and rise and rise and would converge actually as an asymptote to this EE locus here. So education would rise along the transition and would become rather high, at this point as high as it is drawn here, and then we would observe economic growth, sustained economic growth. Here we would still observe stagnation because the low technological progress that we have here is offset by population growth, so incomes would not grow at this point. Now, the point here is that if the economy starts to the left of this locus, which it does actually because it started with a low income level, there would be no way of getting beyond this intermediate equilibrium here. So the economy would still be trapped in the poverty equilibrium, although there are in principle multiple equilibria possible now. So the poverty trap is not anymore a global equilibrium, but for the initial conditions with which the economy started, it would still converge back to the stagnation equilibrium when there is a small perturbation of its income, say due to an income shock or a certain invention that increases productivity at one point. But if this invention only has a low effect on incomes, the economy would not be pushed out of the basin of attraction of the poverty trap. However, when the population size increases by even more, and when we are then in a large population case, then this curve GT plus 1 shifts upward even more. So, and then it would intersect with the ET plus 1 curve only once anymore, and this would be in the interior of the figure. So then there would be only one equilibrium left, where education is strictly positive and technological progress is rather fast. And now the economy would be able to converge to this equilibrium because there is no poverty trap equilibrium anymore. So actually, the poverty trap has vanished endogenously for this large population size. In terms of the full model dynamics, it would mean that there is only one EE locus here. The XX locus is located here, the conditional Malthusian frontier here, and the dynamics are such that the economy would start to experience increasing education and increasing effective resources here in all, in this area here, and in this area also. If it is to the right of the EE locus here, education would decrease, but effective resources would still increase, and only here we would experience a fall in effective resources, basically. So in this case, the dynamics would be that the economy experiences sustained economic growth. And if you are in this quadrant here, we would converge first down, but then you would experience growth. So that's now sustained long-run economic growth, because now there is only one stable equilibrium, and the economy converges to the stable equilibrium, and this stable equilibrium is associated with per capita GDP growth because technological progress is fast and income and fertility are not anymore positively related as they would be when the equilibrium is below the conditional Malthusian frontier. But that's not the case here. So the demographic transition has happened, and further increases in income do not raise population growth anymore. And that now explains the escape from the poverty trap, from the Malthusian trap. It explains the Industrial Revolution and the demographic transition. So initially, we would have a small population size, a low rate of technological progress, and we would be in the Malthusian equilibrium where the economy stagnates. The low rate of technological progress is not enough to overcompensate for positive population growth in terms of effective resources per worker, and that means that all gains in income that are driven by technological progress are fully offset by increases in the population size. That's exactly what Malthus predicted before the Industrial Revolution. But this slow technological progress over time leads to slow population growth. So the population becomes larger and larger because technological progress leads to higher fertility, and that increases the population size, and that gradually shifts upwards the curve of technological progress as being dependent on education and the population size. So initially, a globally stable poverty trap would then start to vanish endogenously due to population growth. So population growth acts as a latent state variable that changes the properties of the underlying dynamic system. So as population grows, that would then lead to two locally stable steady-state equilibria, the Malthusian trap, poverty trap, and the modern growth equilibrium. But the economy would still be in the Malthusian steady-state because it started there. So it's not yet in the basin of attraction of the modern growth equilibrium. But then, if the population size grows further, which it would in this economy, the Malthusian equilibrium would vanish completely, and it would vanish endogenously, and there would be convergence to the modern growth equilibrium. And that's exactly what I've showed in the previous graphs. That's exactly the dynamics in the Galor model of unified growth theory. So finally, we can now explain the long-run evolution of the different economies in both regimes. So we would have the long-run stagnation equilibrium that is explained by the dynamical system for a low population size, small rates of technological progress, and a positive association between income and fertility. And then endogenously, this equilibrium becomes first not anymore the globally stable equilibrium, but there are multiple steady state equilibria that become possible. And then endogenously, the stability, actually the Malthusian equilibrium becomes unstable, and the modern growth regime becomes the only stable equilibrium. And that's when the economies start growing. The positive association between population growth and income growth breaks down, and per capita GDP and these effective resources in the model and incomes start to rise, and this happens in a sustained way. So this was now in essence the main insight from unified growth theory as invented by Oded, Galor and David Weil in their seminal 2000 paper in the American Economic Review, and as elaborated upon further by Oded Galor in his longer article and in his book. Special thanks for this chapter to Katharina Werner of the University of Göttingen for all the discussions and exchanges that we had on the unified growth model, and for providing such nice illustrations. Thank you.